Right, this particular video, it's kind of wordy, so read that paragraph to yourself, pause it. I highly suggest you read it so you get the or a good sense of what's going on. I'm just going to give you the quick summary here. Here we have a block that starts at point or at this location here where the dashed line is. It's going to get pushed to the left, compressing the spring with some K constant here, and then it's going to be released. It's going to shoot to the right. It's going to go across point A to B, which is rough because there's a coefficient of kinetic friction there. And then it's barely going to make it all the way up to C. Okay. The question wants us to find how far do you have to compress the spring in order for it to barely make it up to point C and carry over. All right. Keep that condition in mind. All right. So other than that, I'm just going to go with cracking. For this particular problem, I'm going to treat this location here as my initial reference frame. And then at the top of the loop at point C, my final reference frame. Okay. All right, here I'm going to set up MEI minus the work due to friction, which is equal to MEF. So keep in mind, here's my initial reference frame. The initial energy is going to be stored in the spring. It's going to go across this segment AB, which is rough, which means mechanical energy will be taken away from the system. Okay, so there's mechanical energy, quote unquote, loss here due to the work of friction. So I'm going to take the energy here, which is the initial. I'm going to subtract it from what I'm about to lose from segment AB. And then as it goes up to point C, it has mechanical energy, and that will be composed of PE and KE. Why? Because it's above the ground and it's going to be moving because the problem wants us to find where it barely makes it over, which implies that it's still moving. Okay? All right, let's go and do it. So hence my starting point here is the initial mechanical energy compressed in the spring minus the work due to friction across segment AB. And that'll give me the leftover, which will be converted to ME at the point C here at the top of the loop here. So if I were to break it down, okay, and include everything, right? ME is composed of P due to gravity plus KE plus P due to spring. But you notice here in my statement, I'm going to subtract all that for the energy loss at segment AB, which is the work due to kinetic friction. On the right side, I have all the same term except with an F subscript. So P due to gravity final, KE final, and then P spring final. But this is my starting point, but you hopefully will learn to cross things out as you practice. On the left side, I've crossed out P gravity. Why? Because the box is on the ground to start. Okay, so there is no height. If there's no height, there is no energy stored in the system due to gravity because PE gravity depends on height. Well, I'm also going to cross KEI out because if you pause the video and read this paragraph like I suggested, it says here the block is initially at rest, which means there is no kinetic energy. Well, like I said earlier, right, it's asking us to find the distance that the spring must be compressed for this phenomenon to occur, which implied that there is energy stored in the spring. So I think PE springs stay, and that's a no-brainer. Minus due to work of friction, once again, because as it goes from A to B, it'll lose some energy. The rest of it will go to point C. At point C, though, there is a height, so I want to keep PE gravity. It is moving, so I want to keep KEF. I want to cross out PE spring because at point C, there is no spring. Spring was over here to start the problem. So as you can see here, while this function is kind of extensive, you can simplify it down to quite a bit. What I want to do is I want to just replace PE spring for what it is. It's 1/2 kx squared. The distance compressed or stretched. In this case, the distance compressed is just called d. So instead of x, I'll just use d because the diagram uses the letter d. Minus the work due to friction. MGH here is for PE final. Why? Because there's a height. Okay, there's a height from ground up. And then KE is 1/2 MVF squared. VF here being at point C. So here, I have a bunch of stuff already. Okay. What I can do though is find how much work is lost due to segment AB. Well, here I drew the box. Okay, or I just carry the same box over. So as it travels across this rough surface, there's energy loss. Well, how do you find work loss? Well, the work due to friction is contributed to just the kinetic frictional force times the displacement. So here I can just break it up. As the box is moving rightward, the frictional force, F of k, will be pointing leftward because it's acting against it. Well, here, I can replace F of k with mu k F of n times displacement. Okay, so really, this whole statement just get carried down, except wherever F of k is, I need to substitute it out for mu k F of n because the problem gives me mu k. Well, I don't know what F of n is, but that's okay. This is light work. you can just draw the free body diagram here. Well, the box is touching the rough surface, which means there's an f of g pointing downward. At the same time, though, in the y direction, there is an f of n pushing upward on the box by the surface. And these two have to equal in magnitude for this particular segment because there's an arrow down and there's an arrow up. And the acceleration in the y direction is 0, which implies that the magnitude of these two vectors have to equal. So what I can do is I can substitute out for f of n for f of g because they are indeed equal in magnitude. Okay, so instead of f of n, I can substitute out for f of g, but f of g by definition is just mass times gravity. So that quick substitution there, hopefully by now, you're familiar with that. Other than that, I'm just going to plug the stuff in. The coefficient of kinetic friction is given as 0.28 in the problem. M is 0.5 right here in the paragraph. And then G here is negative 9.8 because the frictional force in this particular diagram is pointing leftward. So the negative 9.8 there compensate for that. Delta X here is given here in the wording. It says the length of AB is 2.5 meters. So I'm just going to plug and chug. And if you do your calculator work correctly, you should get a negative value of 3.43 joules. And negative 3.43 makes sense because it's energy, it's mechanical energy taken away from the system, right? So therefore, I know what the work due to kinetic friction is. It's 3.43 joules. Here, I can just substitute out for a lot of stuff, okay? So just keep up with this next few minutes here. W f of k, I replace with 3.43. Keep in mind that I'm already telling you that the energy loss is negative, so I don't need to use another negative sign. So the negative work down here is simply to show you that it's energy loss. But the negative sign is already introduced here, so don't plug in another negative. Otherwise, you end up adding, which makes no sense, okay? You're taking energy away from the system, so you have to subtract. All right. On that, I'm going to leave units out. K is 100. The problem said so. D is my unknown. That's what I'm trying to find. M here is 0.5. G is 9.8. This is positive 9.8 because we're dealing with energy here, which is a scalar. HF here is 2.4. And then mass here is 0.5. And then VF here, I don't know. I don't know how fast it's moving at point C. Now, you notice here I highlighted 2.4. That's because hopefully you can do your geometry, or not your geometry, you can do your measurement correctly. Here, H is measured from ground up, okay? So from ground up to point C, that's the diameter of the circle. It tells us that the radius is 1.2 meters. So therefore, the diameter, which I would just call height here, must be twice the amount. So 1.2 plus 1.2 is 2.4, or you can just do 2 times 1.2. It's up to you. So that's where the 2.4 comes from. So as you can see here, the only thing really left as unknown is d squared and vf squared. But I'm trying to solve for d squared because ultimately that's what I'm asked to find. How far would you have to compress the spring so that this occurs? Okay, so I'm just going to simplify it by getting rid of vf squared. Well, at the very top, okay, typically when an object goes in this vertical loop-to-loop, there's an f of g pointing downward because f of g always points down the page. But at the top of the loop, when the object's on the inside of the loop, the contact force is pointing down as well because the track pushes down on the box. Here is f of n. That's typically how it's done. However, I do want to point out the statement that's super important. It says here in the statement, just barely make it through the loop at point C. Anytime you read those statements, it's implying that it's a minimum value. Well, here you have two vectors at the top of the loop. You have f of g and f of n. In order to make this a minimum, you have to get rid of f of n. Barely make it over would imply that it's about to lose contact with the track, okay? So if it doesn't, then you have two vectors. But if these types of wording is used, you need to get rid of f of n. So really at the top of the track now, there's only one force acting on the cart, and that is f of g. You cannot get rid of f of g, okay? So therefore, I can just say that the centripetal force here at the top, because it is moving in a vertical loop-to-loop, which means it's moving in a circular shape, which means there is centripetal force, I can simply say the centripetal force is f of g, because f of g, it is the only vector left now pointing towards the center. By doing so, I can break up f of c into mv squared over r, which is equal to mg. But as you can see here, both sides has an m. I want to cancel that out. Therefore, I can solve for v squared by multiplying both sides by r. So you see this r down here? I'm just going to get rid of it by multiplying both sides by r. But here, this is v squared. But keep in mind, this is v min, okay? This is the minimum velocity that it needs, okay? Not max, because anything greater than this will work. So this is v min. Even though I didn't put a subscript here, Because I got rid of f of n because it says barely make it through the loop. This is the minimum speed that you must carry in order for you to make it all the way around. Therefore, I'm just going to plug in g being 9.8, r being 1.2. I left out the units here. And that v squared will give you 11.76. Here, I'm not going to square root it. Why? Because over here, I need vf squared. So I'm just going to keep this v squared the way it is. So I'm just going to substitute it out for over here. Okay, once again, I'm not square rooting it because I need v squared. So why square root it and then square it again? So therefore, vf squared is simply 11.76. So I'm just going to substitute it out. Here, 0.5 times 9.8 times 2.4 gives you 11.76. And if you punch in 1/2, times 0.5 times v squared, which is substituted out for that, you'll get 2.94. But you notice here, you used to have this term on the left side of negative 3.43 joules that you lost from segment AB. I'm just going to do a couple steps here. So we're going to add this. Watch my cursor. We're going to add 11.76 to 2.94. But at the same time, we're going to add 3.43 because this is negative 3.43. So when you move it to the other side of the equal sign, it changes sign. So it becomes adding. So I'm just going to say 50d squared is equal to 11.76 plus 2.94 plus 3.43, which will give you 18.13 on the calculator. Well, here, as you can see, we have d squared. So to get d by itself is super easy to do. The next step is to divide both sides by 50. So if you punch in 18.13 divided by 50, you'll get 0.3626. But this is d squared. So therefore, to get d by itself, we square root. So the square root of 0.3626 will give you a value of 0.6 or about 0.6, okay? And that is your answer for this particular problem. So the minimum compression needed is 0.6. And if you compress it any more, if you compress it greater than the value of 0.6, then it will make it all the way across because now you're adding more energy to the system. And with more energy, it'll shoot out faster. And if it shoots out faster, it'll have more energy left over, which means it'll move faster at the top, which means it'll make it over. So, okay, I hope that makes sense. Stay nerdy, don't be whack.